Okay, here's part 2 of the video on factor analysis, picking up where I left off on the previous one. I was having some technical issues, so um, moving on. Through the document here, I put up the table of correlations and the outputs from SPSS so that you can easily see it. But let's move on to some other material. The previous pages show the preliminary computational steps in principal component analysis, just computing the factor loadings of the variables onto the first factor that was identified. And that's just scratching the surface. There's a lot more to go into in factor analysis. It's a deep topic because there's so many different versions of factor analysis. It gets pretty confusing to a lot of people who practice factor analysis. But the key point to remember, as stated by Larry Price in his psychometrics textbook, is that factor analysis involves the, quote, exploration and identification of a set of variables in terms of a smaller number of hypothetical variables called factors based on the patterns of association within the data. And I would add that the patterns that we're looking at are from the correlation table. Here's some terms that I derived from 3 of the 4 different books that I mentioned at the very beginning. Paul Klein's book, Fabriger and Wegner's book, and Petlacki and Sullivan's book. You've got common factors, unique factors, which are then divided into specific factors and error measurement, and then the relationship between these. And so starting off at the top, a common factor, this is an unobservable construct or latent variable. That's the thing that we're trying to measure in terms of the latent variable. That's the, when we create a scale, these are the things that we're trying to access. The latent variables are the things that we're trying to access. And so the common factor is the behavior in the items that's all attributable to or caused by the latent variable. So the unobserved construct or latent variable exerts linear influences on more than one variable in a scale, more than one item in a scale. There may be several common factors, depending on how many factors your factor analysis identifies. That's how many there will be. But there may be several common factors, and we don't know how many when we first start, that exert influence on the variables in a scale. And any individual variable or item in the scale may be influenced by a combination of several of these different common factors. And the way that we identify those common factors is through the common variance or the shared variance within the correlation table itself. Next, we have the unique factors. Each item on a scale, which is representative of the behavior of our subjects, each item on the scale is influenced by unique factors as well as the common factors. So the common factors, you can think of the psychological construct that we're trying to tap into, and the unique factors are whatever's left over. After you take out the psychological component that we're trying to capture, whatever is left over is unique variance or unique factors. And so these unique factors are not part of the common factors, and they may be aspects of influence that affect only behavior on a certain item. So each item may have its own various different unique factors associated with it. Thus, unique factors are unobservable sources of linear influence unique to each item. Unique factors can be divided into these 2 different components, specific factors and error measurement, where specific factors are thought of as systematic sources of influence on the variable or item. And this could be something related to the wording of the item itself. So that if you have an item that artificially elicits from your participants a positive response or a high score, that's something that is not attributable to the psychological construct that you're trying to measure itself, but rather it's based on the wording of the item. And every time you use the scale, you're going to have a similar amount of positive influence based on the wording or phrasing of that particular item. So leading questions that push people to answer in a certain way, you can say that that is a specific factor uh, in terms of a part of the unique factor, which is a type of error. It's systematic in the sense that people will answer in that direction every time you use the scale because of the wording of the item pushes people in that direction. So it's not truly random. Where random error, people would score high or low and it would cancel out over repeated administrations of the survey. If it's a specific factor, it's going to be pushing people in one direction every time you use the scale. And in that way, in that sense, then the reliability of the scale will not change based on a specific factor source of unique variability, but it's still not a valid measure. So it doesn't affect a specific factor of this nature does not affect the reliability of the scale, but it does affect the validity of the scale. And then the second type of unique factor is error of measurement, which is true random error. If the phrasing of the question itself is highly ambiguous and people can't figure out what it is you're asking, sometimes they're going to put high scores and sometimes they're going to put low scores, and that would then be true random error, which would cancel out and cause a lower value for the reliability of the scale. Both of those would affect the variability, or rather the validity of the scale. And then here's some relationships between these. The observed, what we call the observed variance, that's the actual variance of the scale, is a combination of common variance plus unique variance. That's everything on the scale. Unique variance is specific variance plus error variance. Communality is common variance divided by observed variance. And what we call reliability is the combination of common variance plus specific variance divided by observed variance. The figure here comes from Fabriger and Wegner, and we see 6 items, 1, 2, 3, 4, 5, 6, each of which has a circle underneath it that represents unique factor or unique variance. That's this part. Part of this is going to be specific based on the wording of the question that might push people in one direction or in a different direction, and part of it is going to be true random error. So we don't know based on this whether it's truly random or whether it's systematic error. And we see in this particular example 2 different common factors which exert linear influences on all 6 of the items. Here I want to talk about the 2 different families of factor analysis. Actually, if we back up a little bit more, we also have exploratory and confirmatory factor analysis. Where confirmatory factor analysis, I'm not going to cover that here. I'm only talking about exploratory factor analysis, or EFA. But there are 2 different families of exploratory factor analysis. So we can divide this down these 2 pathways. So we're not even talking about confirmatory here, just exploratory. And we see that we have lots of options in front of us. The 2 families, on the one hand, you have principal component analysis. That's what I computed by hand. And on the other hand, you have what's called quote factor analysis, or sometimes it's called common factor analysis because you're looking for the common factors, or non-iterated principal axis, NIPA, or principal factor analysis, which is also called, synonymously called, principal axis factoring, and that one is in SPSS. Also iterated principal axis and maximum likelihood. So of the different versions of factor analysis here, and these aren't even all of them, there are many more, principal component analysis is probably the most common. And I think that's an artifact caused by historical reasons, that it was historically the easiest one to compute by hand. And before computers were developed that could run factor analyses easily, when people had to do these by hand, this is what they chose. After computers were developed that could, with programs that could handle this stuff, people who wanted to do factor analyses did not know which version to use because of lack of authorities in the published literature, and they looked to see what previous generations of researchers used, and they saw that those researchers used principal component analysis, so people just kept on doing principal component analysis, which may not be the best method. I like principal axis factoring, and I'll say a few words about why. Principal component analysis deals with the brute force reduction of correlations into a smaller set of clumps with no regard for theory, and PCA was not designed to identify components that are directly identifiable as meaningful latent variables. The components may have little intrinsic or theoretical meaning. It just parses the numbers. It's purely mathematical, and it analyzes the variance. Whereas this branch of factor analysis deals with the difference here, components versus factors. I use these two terms synonymously, but I probably should just say factors. Common factor analysis, or CFA, which is not to be confused with confirmatory factor analysis, which is CFA also. Common factor analysis and its variance, all of these are types of common factor analysis, are more practically sensitive to theoretical issues when the analyst understands factor analysis. Factors should be cleaner in the sense that they deal with items with high communalities. So you're going to get higher scores in the factor loadings here. The rotation is such that you're going to end up with essentially stronger factor loadings in many cases. Another, and I don't want to go through all of this, but another difference here is that principal component analysis assumes that your underlying latent variables are not correlated with each other, whereas common factor analysis allows you to have correlated latent variables. And in psychological research, I think it makes sense to have correlated latent variables. And so for that reason alone, I think it's optimal to use some version of common factor analysis. And going through these different books, the Fabriger and Wagner, and the Petlacki and Sullivan, and the DeVellis and the Klein book, the thing that stands out as being common among them is that they recommend principal axis factoring when you have correlated latent variables. And so this is what I like to use. Fabriger also argued in this publication here in Psychological Methods that although the vast majority of people in psychology who report factor analysis use principal component analysis, they probably should not. That they're doing this in error. So when I ask you in class to do a factor analysis, I'm going to be asking you to do principal axis factoring. And in terms of the rotation, there's some different types of rotations, and I like direct Obermann is the best. So here's some considerations in terms of how to interpret a factor analysis, and then I'll run it and show you in SPSS. So how do you evaluate the output? Well, let's first look at the correlations. Here's a different scale one that I developed. So this is a different data set that I have from a number of years ago, data that I collected online. And we've got a correlation table. You don't want your correlations to be too low, neither do you want them to be too high. It's kind of like the three little bears. Here's one that's very high, and so that may be problematic, but you can see that it correlates less highly with others. Here's one that's pretty low, and that might be problematic, but we can see that this item number 37 correlates a little more highly with some of the others. So it's okay if you have a few correlations that are very high and a few correlations that are very low, but if you have too many of them, it's going to ruin the analysis. So according to Petlacki and Sullivan, any correlations greater than 0.80 are problematic. So you want to look in your correlation table to see if you have a lot of correlations that are too high, like 0.80 or above, because what that means is that the items really are the same thing. If you have a correlation that's that high, it means that there's just one or two words that are different in the item, and people are interpreting the item in the same way. When you have a bunch of items like that, what's going to happen is it's going to ruin the matrix, so then you have a whole bunch of trouble as the people living in the matrix come to terms with coming out of the delusion of being in the matrix. But actually what happens is that SPSS gives you an error message when this happens. And so you get what's called a singular matrix. And the error term says matrix is singular, not positive definite. In class, when I've asked people to, in psychometrics, to devise their own scales and collect data, the data sets sometimes are pretty small, but they had high correlations because the items were so similar. And after seeing this error a few times, I couldn't figure it out for the longest time, for a couple of years. And then I finally found a source that told me about it. And I realized what was happening is that the items in their scales were just repetitions of each other. And so people were not taking it seriously. You had the same answer for everything. And so the whole thing, the whole matrix sort of exploded. It didn't work. SPSS refused to run it. So that happens. You want to take out any of the items that are correlating above 0.80 with multiple other items. Similarly, you don't want the correlations to be too small. What happens then is that you get an identity matrix. So it's a similar situation, but in reverse. The items are so unrelated to each other that you'll get the same number of factors as the number of items. This is relatively rare. It only happens when you have items that are really, unlike each other. And so they have no business being in the scale together. And when this happens, it'll get flagged in Bartlett's test of sphericity. In Petlacky and Sullivan's book, they do not give guidance on how small is too small for the correlations. But generally speaking, the whole point of factor analysis is that you want to have a starting point where you have a correlated set of items, and you want to boil them down into something more manageable. So uncorrelated items shouldn't be together in the first place. It's okay to have a few small correlations, but you don't want too many. So there are several different diagnostics that we can run on the data set. Bartlett's test of sphericity tests the null hypothesis that the correlations are 0. So we want this to be significant, but just having it being significant doesn't really mean that much, because it's almost always going to be significant. But if it fails to reach significance, then you know you have a problem. So having Bartlett's test being significant is sort of like having a green light that tells you you can keep going. If it's not significant, it's a red light, and you have to go figure out what's wrong with your scale because the items are not correlating with each other. So this test is directly impacted by sample size and the number of items. So it's sort of artificial. It's not the greatest test, I think, but it's important to check it and make sure that you have significance here. Next is the Kaiser, Meyer, Olkin test, and this is a measure of sampling adequacy of your items themselves. It's kind of like the Bartlett's test in terms of giving you permission to proceed with your real analysis. This is just a gateway test. Higher KMO score is better, and it's a little bit subjective. I mean, you can get by with a little bit of mischief here with some low KMO scores. You get a single KMO score for the scale, and there's a way to also get individual KMO scores for the individual items. So this test, this statistic, crudely speaking, is the sum of the squared correlations divided by the sum of the squared correlations plus the sum of the squared partial correlations. And so I'm not going to do the formula here because it's not really that important. But when the correlations in a table are high overall, the KMO will be close to 1. Whereas when the correlations in a table are low, excuse me, when the correlations in a table are too low, then the KMO score would be close to 0. So it's doing sort of the same thing as Bartlett's test. If you have high correlations, you're going to get the green light to go forward. If you have very low correlations, then you're going to not pass. But you want to be able to pass both of these. Next, you have the sampling adequacy and the anti-image matrix. Probably you never heard of the anti-image matrix, but SPSS does it for you, so it's easy. In the anti-image matrix, and I'll show you how to do this in SPSS, when you look at the second half, the lower half of the anti-image matrix, the diagonal, which in a correlation matrix, the diagonal would be 1. This is not 1 because it's a transformation of the correlations. The number that you see is the measure of sampling adequacy for that individual item, and that's basically a KMO score for the individual item. So you can interpret that with the same metric as here. Anything less than 0.5 is unacceptable. So you want to see a number that's 0.5 or greater. And then in the off-diagonal elements, you see what look like correlations, but they're not. The off-diagonals are the negatives. If you think of film negatives, you have the basic idea. It's the complement of the partial correlations. So these numbers are going to be small. You want them to be small, and smaller is better. Ignore the negative signs. Just look at the absolute value. There's no real rule for this, but the anti-image of the off-diagonal elements in the table, if they're greater than 0.2 in absolute value, they could be problematic. It could be a sign that it's a bad item. If you have a whole bunch of values that are greater than 0.2, then the scale may be a bad scale. So let's pause for a second and actually take a look at how this would work using SPSS. I'm not going to increase the screen this time because that gave me some problems last time I did it. So to do factor analysis, we go to dimension reduction factor. And this time, let me reset it. This time I'm going to use all 20 items in the RWA scale. I click descriptives, and you want the anti-image right here and the KMO and Bartlett's test. That's where you find these two tests that I just mentioned. And then for the extraction, I want to see the Scree Plot. And this time I'm going to switch from principal components because I don't like that, and use principal axis factoring instead. This is the one you should be using for most psychological research. And I click OK. By the way, if you wanted to change the value of the eigens, if you wanted to eliminate the number of, like if you had too many factors and you wanted to stipulate I only want 3 factors, you can put that in right here. But we're not going to do that. We're going to go based on the eigenvalue greater than 1 rule. But you can change that number right here. So we click continue, and then we want to change the rotation to direct Obermann. I know this is a lot of choices here, but this is the one pathway that I recommend. So principal axis factoring for the extraction and direct Obermann right here for the rotation. And then you're good to go. I don't think there's anything else here that we need. Yeah, that's it. So we click OK. And then we have this gigantic table. Well, actually we have a small table first. So here's the KMO and Bartlett's. You see the KMO score is high. It's very high. And we wanted, the highest value on the scale. If we go back to the page, 0.80 is meritorious. Anything above 0.80 is, outstanding. And we can see here that the KMO score is 0.944. So that's very, very high. And the Bartlett's test of sphericity is significant. So both of those give us the green light to go forward. Here's the anti-image matrix, and this is what I meant by you want to look at this the lower half. This is the part you want, not the covariances, but the correlations. And along the diagonal where you see the letter A next to the number, that is the individual KMO score for that item. So for RWA item number 1, we have a KMO score of 0.947. That's very, very high. And then all the off-diagonal elements, you can see that the numbers are very small. And that's what you want to see. You want to see really small numbers here. And there's nothing here that flags any of the items as being problematic. And like I mentioned earlier, Bob Altmeyer has done years and years of tweaking of the scale to the point where it performs as good as any scale I've ever seen. And so there are no problems indicated in this part of the diagnostics. We go down to the eigenvalues. We can see that there are 3 factors identified. Meyer predicted that there would be 3 factors: authoritarian aggression, authoritarian submission, and conventionalism. So that's good news for his scale, because SPSS is telling me I've got 3 factors. There are 3 eigenvalues greater than 1, and each of those has at least 5% of the variance explained, and so that's good. We've met both of those criteria. And then when we look at the Scree plot, this is a little bit weird. So the Scree plot is not in agreement. The rubble, where the rubble ends, right here, that tells you where the factors begin. So we would stop it here. From here to here is factor 1, and from here to here is factor 2, and that's it. So according to the Scree plot, which was, this technique was developed by Hans Eysenck, according to the Scree plot, there are only 2 factors, so the Scree plot is not in agreement with the numerical aspect of the identification of factors. According to the math, we have 3 factors. According to the Scree plot, we have 2 factors. So, I don't know. When that happens, the researcher has to decide whether it makes sense to go with the greater or the lesser number of factors. In this case, I think it makes sense to go with 3. Okay, so we've done principal axis factoring with direct Obermann rotation. And we've got 3 of these tables down here. We don't know which one to use. Well, the one that you want to use is called a pattern matrix. And the thing here to do is to identify which of these factors each one of these items loads onto. Now, RWA1, that was the item about having a strong leader who's going to stamp out all the wicked people. And that loads really strongly onto factor 1. The second item was about gays and lesbians being as moral as anyone else in society. And that one is loading onto the second factor, not the first factor. So what you want to see here are clean factor loadings where each item loads only onto one factor. And the factor loading that you want, this is after the factors have been rotated to fit better onto their factor. The data have been rotated to fit better onto the factors. What you want to see is that each item has a factor loading of 0.4 or higher, and it's only loading on one factor. RWA19 is a little bit problematic because it seems to be loading about equally well on both factor 2 and factor 3. Okay, so almost done here, almost done. So I've got the, this is a different data set, the Ohlers Ordinary Life Experiences Rating Scale that I developed. Here's a smaller version of the anti-image matrix. So what we would be doing here is looking at the second half along the diagonal. Those are the individual KMO scores for these 4 different items. And then the off-diagonal elements, those are the anti-image scores for the items. And you can see that this one is too high, 0.735. So that may, if either of these items, item 8 or item 46, does that with other items, then we might want to take a look at removing that item. And so here's some text that tells you about how to interpret the number of factors, the eigenvalue greater than 1, the 5% rule, and the Scree plot. And I'm just going to wrap up here because you can read this part on your own. But I talk about here the way to interpret the Scree plot. This is a graphic from Petlacki and Sullivan's book. And here's from a 43 item version of the scale. It's kind of a hard one to interpret in terms of the number of factors. So I think I'll end that here, and you can read the rest of this on your own. But in a nutshell, that's how you do it. That's how you run factor analysis. Yeah, I think that's the rest of this you can do on your own. But so again, just to recap, the pathway here that you want is dimension reduction, factor, and then the options, principal axis factoring, check the Scree plot. You want to see the Scree plot. Direct Obermann rotation, And under descriptives, you want to get the anti-image and the KMO and Bartlett's test. And now you know how to do that. So, okay. Thank you for being here today. Take care.